Hello everyone, my name is Christodoulides. I'm from the University of Southern California. And as my title reveals, today I will be sharing with you our recent results on optical thermodynamics in nonlinear multimode systems. We'd like to thank the organizers for inviting me here to the party. And of course, also the audience for showing up. On the last day of the conference, any particular deadline for finding the room, I just got lost in this maze, to be honest. So in any event, let me try to put that in perspective. So we are all familiar with all the benefits we reap over the years from nonlinear processes in optical fibers. We use them for continuum generation, for parametric oscillators, high power sources, pulse compressions, optical solutions, and so on. However, if you look very carefully at all these developments that happened in the last, I would say, starting from the 70s, now almost 50 years, most of them, unfolded in single mode settings. So if you read, for example, the Bible of nonlinear fiber optics is mostly an ode to, say, single mode fibers. So, yet, in the last few years, we saw a strong comeback of multimode, say, fibers. And the reason is self-evident. Why? Multimode systems have big cross-sections that can handle high power. So essentially, they're ideal for high power sources. But more so, they provide another opportunity to take a look at all these processes from a new perspective. They may actually have opportunities that we didn't have, say, single mode environments because of complexity. So indeed, as such, starting from 2014 mostly, we have seen beautiful supercontinuum generation in graded multimode fibers with high spectral densities, observed geometric parametric stabilities, new class of dispersive waveforms have been developed, along with the observation of multimode solitons. I may say a lot of these efforts culminate here from the work of Frank Wise, where he demonstrated, for example, mode locking not only in time, but also in space. So you have, say, tens of modes that lock together spatially as well as temporarily. And of course, this leads to record high energies and high power and high powers. Of course, I have to admit that all we have been observing over the years, in the last few years, most of these processes are actually complexifications of what we saw in single mode fiber. Yet, there were certain processes that have no counterpart whatsoever in in previous seconds. And the most notorious of that is what we call eventually beam settling. So what is beam settling? This effect was observed independently by three groups, all reporting the same things, by Creole, by Cornell, and also by Gruber. So essentially what it is the following. Let's say I excite a multimode fiber with very low powers. Of course, I'm exciting hundreds of modes. The interference at the end of the day, at the output, looks like this, highly spectral power. Yet, as I crank up the power, and I reach moderate levels, such as 10, 20 kilowatts, the beam transforms itself from this mess to something considerably more open. So it looks like the beam is clean, but people didn't know what exactly is behind it. Definitely it wasn't self-focusing. Self-focusing is silica requires 4 megawatts. This was observed, say, at 10 or 40 kilowatts. It was a Raman. Why? Because in 2 meters, even the first stop's line didn't show up. So it wasn't definitely a Raman. It was non-linear, but then again, what's going on? So there were several efforts to get to understand it. But the problem is complexity itself. What I'm showing you over here is what's going to take to simulate, say, 2 modes to 2 polarizations. So essentially, you have to, you can go do it in a brute force manner, right? Launch your BP, your nonlinear Schrödinger solvers for every mode and see all these interactions. So imagine now what's going to happen if I have, say, 1,000 modes. Just to set it up, just to set up the code, I need to compute 1,000 propagation constants, 1,000 surface modulation coefficients, a million cross phase and a trillion four-way mixing paths. This I have to do before I even start the process. The other issue is I can really launch a super VPN and project on the modes. It's fine. You see, the problem, however, at the end is not so much if we have the computational capabilities of really following these processes, is how you interpret the results. If you don't know what you are looking at, the mess of 1,000 modes, very soon you're going to get lost. So at some point, we said, okay, we have to really approach the problem differently. So definitely what we want to know is how the power settles. Do we understand it? How we understand this redistribution? Can we really exploit it or modify it at will to our advantage, and so on and so forth? So what we did was abandon the traditional methodologies we have been so used, nicely used, actually it was so costly to use the nonlinear Schrödinger equations for 40 plus years. We're starting from 17, so that will maybe 50 years, right? And instead, develop a thermodynamic theory that's based on the tenets of statistical mechanics. Lots of the program we'll be giving is based on our papers over here. So if you want to know more, all you have to do is consult really some of our recent papers in this respect, where we very self-consistently developed this statistical mechanics or thermodynamics for these particular systems. So what do we need to know before we use this particular methodology? Surprisingly, very, very little. All you need to know is what is the number of total modes supported by the system. Let's say a system, a Viper or a cavity or whatever supports 100 modes. And the other piece of information you require is the spectrum of the linear system. What would be the propagation constants of the waveguide or the eigenfrequencies of a cavity for that matter? If you have this information, in particular, what? The number of modes and the spectrum, you are set to go. The next aspect that you need to clarify is what are the conserved quantities? Because after all said and done, statistical mechanics is about the reallocation of conserved quantities. So if you have a fiber, and I will talk more about fibers because this is conceptualized as opposed to cavities, but all these are concepts that can go back and forth. So definitely, if you have a good fiber, the power is conserved. Meaning, if you launch say 10 kilowatts at the input, you're going to get 10 kilowatts at the output. The other that is not so obvious is what we call the total energy in the system, which we denote as U. U is defined as minus sigma, the sum of the power in mode I. Ci squared is the amplitude squared is the power in mode I times the propagation constant of the node, or the eigen, the eigen value of the mode itself. It so happens that in fibers, this quantity here, this Hamiltonian quantity here, is proportional to the Minkowski, the linear Minkowski electrodynamic momentum. So as you put the light in the pipe, you know what I mean? Even in the presence of nonlinearity, the longitudinal momentum is conserved. We just call it here U. Now, if you are in a cavity, that will correspond really to the total energy in the cavity and so on and so forth. So U, in fact, is proportional to the TZZ component of the maximum stress pressure and so on and so forth. These two come very quickly in systems of this sort, these two pressure conservation laws. If, on the other hand, your fiber is very, very round, then in that case, even the orbital angular momentum is conserved. Then you may have three. But on most occasions, we're going to drop it there because most of the times the fiber has irregularities and therefore evaporates. The OEM evaporates. So now, if you're going to now go ahead with statistical mechanics, the first thing to do is to define a healthy entropy. Well, S, the entropy is the logarithm of all the microspace W. We have no other option but to use that. You see, it's written on the tomb of Boltzmann right over there on the top. So ln W will give you the entropy. Of course, the way to do it, second law of thermodynamics dictates that the entropy has to be maximized at the end So, but they maximize upon constraints, namely the power and the internal energy or momentum that we just said. So I can always break the power in little nanowatts. Say I have 50 kilowatts, I break it into little nanowatts, and then I ask the question, how many different ways I can put these nanowatts in 1,000 different modes? So the problem is how many ways you can put, say, n indistinguishable particles, because you cannot tell one photon from the other, or say green, this is green light, this is green light, you cannot tell what's this, but the modes are distinguishable. So this is a classic problem in combinatorics, all right? And then you, from there, if you extremize really the number, you know, the entropy upon these two constraints, before you know it, you get, of course, the Bose-Einstein distribution. You have no other option. By the way, the Bose-Einstein distribution can be classical. It doesn't require to have an H bar anywhere. It's just, as I said, in how many ways you put distinguishable particles in different boxes. However, there is something very unique about our systems. Let's say you have trillions of nanobots flowing in 1,000 modes. You understand that the number of particles per mode, it would be in the billions. The only way you can have, you know, billions over here would be if the exponent is extremely small. And if the exponent is very small, you can expand it into a Taylor series, and before you know it becomes this one. So you leave the Bose-Einstein, because you're dealing with a classical system, all of a sudden you are confronted with what? A Rayleigh jeans, a classical Rayleigh jeans, as you may have expected from the very beginning. So here you have the Rayleigh jeans, and of course, all right. There's no move. Go ahead. In any event, okay. All right. So the Rayleigh jeans is given over here. The power per modi is given by minus a temperature over the eigenvalue plus the chemical potential. By the way, this temperature is an optical temperature of the optical gas. It has nothing to do with the room temperature. Mu is the chemical potential of the photon gas. Epsilon r is the propagation constant, or maybe the eigenfrequency of the resonance. It's a simple expression. And this should give you actually how the power is distributed between modes. This is your Rayleigh jeans. You can then go ahead and start from the from the Shannon Gibbs entropy, and formally show that indeed the entropy in this classical system is given by the sigma of ln Ci squared. Ci squared again is the power of mode I. It's a classical entropy. So having said that, we are good to go. But before that, you have to now write your entropy correctly in terms of extensive variable. First of all, entropy is an axiom. Entropy must be extensive. If it's not extensive, your theory is good for nothing. In other words, if I double the system, if I expand the system twice, my entropy has to be twice as much. But that means I have to identify the correct, say, what? Extensive variables that go into the entropy. It turns out that the entropy should be a function of U, the internal energy, P, the power, and the number of modes M. So M should be here. By the way, this was people were toying with this idea. And they were using it as UP. They knew that it was not extensive, and for that reason, they looked the other way, and they said, well, maybe it's not maybe it's not equilibrium entropy, and so on and so forth. It took us actually a year to realize that we have to stick this fellow here in order to really make the system, the theory system. Once you have the proper entropy, then you're good to really write down for the first time the fundamental thermodynamic relation. ds is, of course, the differential over here, and then from the differentials, you can formally, define the optical temperature, the chemical potential, and something with, at the time, the conjugate to the number of modes. We didn't know what exactly it was. We just called it, okay, optical pressure. You know what I mean? So, having said that, from here, one can go a few steps forward and derive formally a universal equation of state. it so happens that always U minus mu P equals NT, surprisingly simple, always valid in this particular system. And to some extent, you may say, it's equivalent to PV equals NQBT that you know from high school. Once you have an equation of state, then you can obtain from scratch, you can always predict the temperature and chemical potential the system will settle in if you know the power that you put in the system and the initial allocation of power among modes. If you give me these two initial conditions together with the equation of state, then you can predict the temperature and chemical potential that goes into the reagents, the entropy, and everything else. So it turns out that in principle, you know, this solution is unique and always exists. So there is a uniqueness in existence theorem that is actually written over here. That is actually formally derived based on Bolzano's theorem in analysis. That actually gives you uniquely the temperature and chemical potential of this arrangement. If by any chance you guess it, take it, because this is the only one. Anyway, so essentially you may have positive temperatures in this particular case, favoring the lower order modes. You may even have negative temperatures in these systems, favoring the higher order modes, or it may be infinite, in which case you have equipartition of power among all modes. You have to remember that the hottest possible temperature is 0 minus. So in the energy scale, this is the hottest possible energy. Both of them, by the way, support condensates. However, this one is the hottest, this is the coldest. And here you go from plus to minus infinity, right? As usually it is the case. So now, does it have to be kernel linear? You see, in fibers, we use kernel linearity. The answer is no. The nonlinearity is inconsequential really to thermalization. Essentially, what the nonlinearity does, it creates a chaotic energy exchange or photon-photon collisions. So as the modes exchange randomly, chaotically, and ergodically power among themselves. So it establishes an ergodic environment upon which you can actually move on and build statistical mechanics. So the nonlinearity is inconsequential. You may have such a nonlinearity, you get the reagents. You may have optomechanical, you get the reagents. You may have a cascade Chi2, or you may have either nonlinearities that are artificial. You see, they don't have multi-way mixing representations, right? Because it's step-like. And again, you get the reagents. So what is the nonlinearity doing? It's just the agent that thermalizes the system. Meaning it's like in the morning, you pour coffee and there's some milk, right? And then you use your spoon really to homogenize it. This is thermalization, of course. So, but it doesn't matter, you know, nobody cares if your spoon is made out of silver or is wooden or you use your finger. At the end of the day, it will thermalize as long as the exchange is chaotic. So this is formally shown over here. And of course, the next issue is, does this to some extent make any sense? So let's see what we have recently done experimentally. So for the first time, we observed formally the Rayleigh distribution in a fiber. The Rayleigh has been around by Zaharov from the 90s. It was speculated, even though it was not formally put forward. So for the fact, in these systems, you know, you start with a distribution that is not, you know, of the Rayleigh type, and eventually you get a Rayleigh and the beam subclinic. So you see the beam subclinic is over here. So the beam subclinic, by the way, that I mentioned at the very beginning, is a thermodynamic manifestation. It's a manifestation of statistical mechanics of thermodynamics in this particular systems. So, and you see the dotted lines is what you expect from theory, and the board, of course, the solid lines is what you observe. So very good in terms of theory and experiment. And what is surprising over here is that you can actually, if you want to run the simulation, it takes forever. You can actually predict it in a scenario, you know, just like that, once you go through statistical mechanics. This is work was done with Frank Weiss from Cornell. The next one is work we have done together with Ulf and Mercedes. the whole idea is to really see thermalization in nonlinear fiber loops. The nonlinear fiber loops, artificially, they create a lattice, a mesh lattice in time, right? So if you have a lattice with, say, 50 modes, 60 modes, or whatever, and then you arbitrarily throw the power over there, then you should be able really to see thermalization. So here we see negative, positive temperatures, this is your regime. And interestingly, we see negative temperatures, again, in regimes. Now, negative temperatures in our systems are easy to see. Why? Because they are isolated. In most systems, you don't see them. Why? Because the system is connected to the universe and very soon becomes unstable and the energy falls down. Here, because they are isolated, you can do all sort of things in the negative temperature. So, meanwhile, experimentally, we monitor the entropy. The entropy always increases irrespective of the temperature. In full accord with what we expect from the second law of thermodynamics. The entropy should increase, and once it stabilizes, you know that you have reached thermal equilibrium. So, in these systems, you can actually prove formally that if by any chance, say, the lattice undergoes an isotropic, an adiabatic expansion of compression, in which case the entropy remains the same. It so happens that U over T is constant, mu over T is constant. So this is analogous to PD gamma, remember? You see, so essentially, if by any chance I compress the lattice, in which case U goes up, the temperature should go up. If I expand it, it should drop. Now, in the negative temperature regime, is the other way around. You expand it, it heats up, and whatever. But these are formal results, right? So essentially, it's like when you pump, say, air in your, when you pump air in your toilet, the reason they get hot is because of this. You know what I mean? So in analogous fashion, we have the new laws now for this particular system. And these are experimental results. What is beautiful is that we observe these results in negative temperature environments. This is the first time we see isotropic expansions under negative temperature conditions. Nowhere else was done. Why? As I said, if the spin system, you may throw it up after a few, after a few microseconds, it flips down. There is no time to see the isotropic expansions, compressions. Here you do it just like that. You can do compressions in the same manner, right? In both temperature regimes. And also you can perform experiments like sun and Joule expansion, right? In these systems. Theory and experiment are in full, accord. So we know that everything works in this particular manner. Now, if you have now isotropic compressions and expansions and two isothermic lines, then you can now envision candle-like cycles. You can actually cool or heat a system. So, for example, I can do optical refrigeration. So how can I do it? I have a system over here that is multimode and it's cold. This is hot. This is the hot environment. And then in between, I have another multimode system that periodically expands and contracts. It's like your refrigerator. So upon expansion, it cools down and it sucks momentum, delta U, in here. And then upon compression, it superheats and dumps it on the hot. So this one continuously, this system here continuously cools even the cold system, right? Using these kind of cycles. And of course, what does it mean cold? Cold, if you reach zero, you understand all the power has collapsed on the fundamental nodes. Remember how speckled the beam was? If there is a way to really cool the system, all the power will concentrate the fundamental node, right? In a way that actually favors us for many applications. So now, if the fiber is also circular enough, then the angular momentum is also conserved. In this particular manner, you can start from these fundamental equations, extremize the entropy, and then you find out a generalized relations. So in this particular case, the longitudinal momentum has a temperature, but also the OEM has a temperature. And of course, you have to remember that these quantities are thermodynamic forces forcing either OEM or momentum to be exchanged from hot to cold. So this is dictated by the second law. Always heat, whatever you call it, heat flows from hot to cold. So if by any chance say I have a multimode fighter and I have two circular polarizations, left and right, these two circular polarizations don't exchange power, but however they can exchange because of clock phase, say U, or in that case OEM. So in that case, if they exchange upon interaction, you know, OEM will be exchanged, residual momentum will be exchanged until the temperatures in both quantities are equal. So in that case, this is done again in full accord with the second law, right? And in full agreement with prediction. These are experimental results from Stefan Wolf's group from Rome, indicating indeed thermalization of OEM in these particular systems. The one other thing I would like to stress is the possibility for phase transitions. So what I have just outlined over here is the theory of ideal gases. If the power levels are small, then these are rare gases. If, however, I start cranking up the power, then it's possible to see self-organization. And of course, in optics, that would be corresponding to a solitron. A solitron that is a coherent structure in this framework is actually another phase. It's like you're dealing with a solid. And of course, if you do that, if you go to this domain, then you have to modify the equation of state to involve the nonlinearity, very much so, like in the van der Waals equation. So if you analyze these arrangements, then you start seeing all these discontinuities in the entropy, chemical potentials, and so on, indicating, of course, phase transition. So if you want to see, for example, what these do, that, let's assume I have a system over here involving two circular polarizations where you don't have any exchange of power, but you have exchange of U, of momentum. In one polarization, I set a solitron, in the other one, I have a gas. It so happens the gas is a bit hot. And upon co-propagation, what happens? The gas evaporates now, the solitron, the solid, and both of them become gaseous. And actually, using the theory, you can find out that both of them settle in the same temperature. So you see here the process of optical evaporation, and of course, this is done through the nonlinear component of the Hamiltonian, which corresponds to interatomic forces. The next aspect, of course, is the following. Let's say my gas is cool. Then in that case, a perfect solitron is already at 0 degrees. What happens is this now cools the gas, and two solitrons are reduced over here. So essentially, the gas is so cold that both polarizations solidify themselves. So again, it's done through the interatomic forces. So why this is important? Because I can get a beam like this, and I can actually transform it to something that looks perfectly good, especially for high power applications. I have a high power amplifier with megawatts, the beam is bad, but maybe I can find methodologies to push all the power in the fundamental mode so as to be, aimed at the target. So Joule-Thomson effects, we have now experiments where we can actually see this rapid cooling upon expansion. So you may collapse all the power, say, on the fundamental node, effectively. And of course, if this is the case, cooling beams, that would have applications, you understand where. It's going to be on the high power end, right? You may actually allow us to do beam combining without really using complicated schemes that allow lasers really to what? To say phase lock. So essentially, it's like what you do every day. When you put your glass of water in the refrigerator, you never want to really know the phase space of all the molecules. You just put it over there, the refrigerator cools it down, and you're set. The same story occurs here, hopefully. So, and finally, I will say a few things about the so-called thermodynamic pressure. You have no option, you have no other option but to introduce the thermodynamic pressure. the equations demanded is the conjugate quantity to the number of modes. Like in quantum mechanics, for positional momentum and vice versa, in statistical mechanics, for every extensive variable, we have one intensity. So the pressure P hat has to be introduced because of the fundamental thermodynamic relation. But what is it? What does it really mean? It turns out that the end, you can, if I give you a system, in principle, the question you want to ask is this thermodynamic pressure related at all to the electrodynamic? So if you want to compute electrodynamic pressure, let's say I give you a fiber with 1,000 or 10,000 modes, you can go and obtain mode by mode, each one of them, TE, TM, HE, H, it's a sea of modes. Then you can get the electrodynamic structure or the 6 field components, put them in the Maxwell stress tensor, get the integral, surface integral of the surface, you can get the electrodynamic pressure. No big deal. But is that what we got related to this? It turns out that is yes. The answer is yes. You see, the thermodynamic pressure can be obtained in 2 seconds. Give me the spectrum. Give me U, give me P, I can give you the entropy, the temperature, chemical potential, and you can get even P hat very quickly. It turns out that this P hat is equal to the electrodynamic pressure that I just mentioned, plus a universal piece, a universal component that involves the temperature and the propagation constant of the last mode, of the highest order mode. So I can very quickly obtain this. I can remove this one, subtract it, and right away I have electrodynamic pressure. Notice that I get it even though I don't know the structure of the electromagnetic fields. Even if you have never took a course in electromagnetics, even if you don't know what's a Maxwell stress tensor or whatever, you can still obtain this electrodynamic pressure for free. These are the simulations over here done on the Maxwell stress tensor. The others are electrodynamics. You cannot tell the difference. They are exactly the same. And this is what I find amazing, that I can get results that belong entirely in the electrodynamic field from just statistical mechanics, just to show you how powerful these frameworks are in this particular respect. And with that, I would like to thank you so much for your attention.